Thank you very much, everyone. And I'm really sorry not to be there. I'm very disappointed, but unfortunately, that's how it is. So I am here on Zoom to deliver this talk on modern inferentialism and our commitment to quantifier-indeterminacy. So this is a question, and it's a question for you. I have not found the final answer to this question, so I would be very interested to know what you guys think about it. I apologize to those who have seen perhaps part of this talk before, even though the bit about quantifier indeterminacy is new. A lot of it will sound familiar to some of you, so you can doze or something. Okay, let's get on with it. Is it working? Yeah, great. So let me tell you first what moderate inferentialism is, and by this I mean moderate logical inferentialism. It's just a view about the logical terms of a language. It consists mainly in these two claims. One of them is called moderation. This term is not the Putnam term. It has been used in the literature on inferentialism, but in a slightly different sense. It's just a view about what the meanings of our logical terms are. And this idea of moderation is related to some sort of realism, the idea that the meaning of a logical expression is supposed to be a model or an interpretation. I think the best reconstruction of the view is one that says that the meanings of our logical terms are classes of interpretations or models rather than just a particular model. And this is because, well, if you look at what model theory says, or sets of valuations, or however we give a semantics for our languages, when we do logic, we typically entertain many models, all of which behave nicely with respect to the logical terms. So the idea would be the meaning of negation is a certain class of models, which is the models in which negation behaves nicely, not just one of them, and so on. Other inferentialist views say that the meaning is directly in the rules of inference and so on, but and others just don't say anything about that. But the one I'm going to focus on says the meaning is a class of interpretations, or perhaps some truth conditions that pin down that class. The inferentialism bit is the idea that the meaning of a logical expressions, the expressions of a language, is fixed by the rules of use of those expressions. And moreover, those rules take the form of intralinguistic rules, meaning axioms, ordinary rules of inference that go from some sentences, which are the premises, to some conclusion, which is also a sentence, or meta inferences, perhaps, which go from arguments to arguments or inference to inference, and perhaps it goes all the way up. I don't know. But it is important that we have this in mind. Now, a bit more flesh onto the bones. So I'm gonna try to talk about this view by focusing on our language, first order language, a formal first order language that is intended as some sort of like modeling or regimentation of the declarative fragment of the first order declarative fragment of our language. And this formal first order language is going to contain the symbols negation, conjunction, and the universal quantifier. I am mostly interested in the universal quantifier. These symbols intend to express the usual logical notions that you know. And what are the interpretations I'm going to work with? Well, they're just like models, but the inferentialist here needs to focus on something a bit more broad than the standard notion of model. And why is that? Well, because the standard notion of model assumes that the logical terms like negation, conjunction, and universal quantifier are going to receive standard truth conditions. But we cannot assume this here, because what I want to show you, I want to focus on how this idea that our the rules of use, which take the form of intralinguistic rules, can fix the meanings as the inferentialist, the moderate inferentialist, understands them, and needs to work with an appropriate understanding of model, which doesn't assume that those meanings are already fixed. So instead of working with models as ordered pairs with a domain plus an interpretation function, I work with triples. These models have a third component. That component is a valuation function that assigns truth values to the sentences of the language. I'm going to do everything with constants instead of variables, just to have less clutter. They assign two truth values, T or F, so everything is classical here. This assumption can be questioned. Perhaps this assumption is already slipping in some meaning into the terms of the language. We can discuss this. Of course, I'm not wedded to this view, just presenting it. One important constraint on what the valuation function of these models does is that it treats atomic expressions the usual way. So an atomic sentence is true if and only if, the same clause that you always see in classical model theory. But otherwise, these models can assign any truth values to any sentences as they wish. For instance, a sentence and its negation can both have the same truth value in a model. That is totally permissible. So now that we have those models there, how can whatever rules of inference we follow regarding the logical terms fix a subclass of those models, the right one, right? How is the mechanism? And the mechanism, our moderate inferentialist says, is typically charity. Whatever meaning constitutive rules we have, they will be correct. So whatever rules constitute meaning in a language, rules of use, they will have to be correct. And that's the mechanism. So the correctness of an intralinguistic rule depends on the nature of the rule. As I said, these could be axioms, ordinary inferences, meta-inferences, and so on. So I'm going to give you examples in each level. For axioms to be correct, it just means that they're true. So how does an axiom constrain this huge class of interpretations? Well, it just constrains it to those in which the axiom is true. And so we can say that an axiom fixes a class of interpretations, the class of interpretations in which the axiom is true. So many axioms can fix the class more and more, right? Here's an example. You have the law of excluded middle. It would impose the following constraint that we have here on models. Every model in the constraint class will have to assign T to every instance of excluded middle, and therefore the class that the law fixes is the class of all models that assign T to this guy. For ordinary inferences, it's not too different, but as you can expect a bit, they are correct just in case they're truth-preserving, and so they constrain the class of models to those that in which, if the premises are true, so is the conclusion, or they rule out models in which that's not the case. The premises are true, but the conclusion is not true, or some instances are like that. So in other words, it fixes the class of interpretations in which the rule is valid. And here's an example. Here's a rule. I'm going to call this negation elimination. This is going to come up later. Sometimes we call it double negation elimination. It doesn't really matter. It's just a name. It allows us to eliminate the double negation, and it imposes this obvious constraint on models. It says, well, if a double negation is true in a model, then the sentence without the two negations at the beginning is also true. And the class of interpretations that gets fixed by this rule is the class of models that respect this, for which this holds. With meta-inferences, which are very important, as we will see, the situation is slightly different. The correctness is more controversial. Different proposals have been made. I defended the proposal I'm going to talk about here elsewhere. I can talk a bit more about this at Q&A. So I'm going to say that meta-inferences are correct just in case they are validity preserving, meaning, so a meta-inference goes from some inference to some other inference, perhaps, or some inference to a sentence. And the idea is that, well, if the premise that is also an inference, all the premises are all valid, then so is the conclusion, right? That would be the idea. Things are not as nice with meta-inferences as they are with ordinary inferences. And the reason is that they don't impose a local constraint on interpretation. So if we look at the constraint that this rule imposes on models, you just need to check whether, you just look at each model and see if this conditional holds. Right, so I was saying that when it comes to meta-inferences, things are a bit more controversial because there are different ideas. People have different ideas of what counts as a correct meta-inference. I am going to use an approach that's called global validity, and it's the idea that a meta-inference is correct just in case it is validity preserving. So a meta-inference goes, here's an example of a meta-inference, just to make it quicker. This is what I'm going to call introduction of negation. It says, well, if this inference holds, so that if the inference from gamma and phi to psi holds, and also the inference from those to not psi holds, then this other inference holds from gamma to not phi. So it's some sort of reductio. This meta-inference is correct according to my understanding, which I have defended elsewhere, and I'm willing to discuss at Q&A, just in case whenever both premises are valid, the conclusion is valid as well. And this is the constraint, therefore, that this meta-inference imposes. And here I'm calling it V negation introduction. In general, meta-inferences impose meta-constraints of this sort. If the premises are valid, then the conclusion is valid. These constraints are different from the constraints imposed by standard inferences, ordinary inferences, and in the sense that they're not local. Like if we look at the constraint imposed by this standard ordinary inference, we see that we can just look at a model and see if it satisfies the constraint. Whereas here, the constraint is imposed on classes of models, not in models individually, right? So they're global. And the problem is that being global, these constraints might not determine a unique class. For instance, to satisfy it, one might have a lot of models that make it so that the premises are not valid in some cases, in the relevant cases, or one might subtract a lot of models so that the conclusion is valid. So there are different ways of satisfying this constraint. These constraints of this kind might not pin down a unique class. And this is going to come up later. Can everyone hear me? Is everything all right now?
Yes.
Cool. Okay, so now, moving on, I'm going to talk about perhaps the most serious challenge that moderate inferentialists face, and it's known as Carnap's categoricity problem. This is a very old problem. I'm just going to tell you about it quickly and show you how it affects the meanings of quantifiers. So look at these beautiful truth conditions. These are the intended truth conditions for negation, conjunction, and the universal quantifier. The first two should be super familiar. So you just say what you expect, and negation is true. If sentence without the negation is false, and vice versa, and so on. The only one that might be a bit weird is the one for the quantifier, the universal quantifier, that says that a universal claim is true just in case an arbitrary instance, so an instance given by a constant that doesn't occur in the formula phi here, is true not only in this model that we're talking about, but also in every other model that is identical to the original model, except that the value of C is different. And of course, because now models include valuations, the truth values of sentences containing C might also differ. But the models M and M prime, so this says M and M prime have the same domain and assign the same interpretations to everything except for C, and the same truth values to everything except perhaps for some sentences containing C. So this clause expresses the objectual, what we know as objectual truth conditions for the universal quantifier. There's a proviso there, but it doesn't matter. We can get into that later. It's not very important. The idea is that, well, a universal claim is going to be true then, just in case every object in the domain of the model satisfies the condition. What the moderate inferentialist typically wants is that whatever rules of inference we follow regarding negation, conjunction, and the universal quantifier entail these truth conditions, or in other words, that they fix this class of models, the class of models that satisfy these truth conditions, exactly those. All the models and only the models that satisfy those conditions. This is what the moderate inferentialist is really hoping for. These are the intended truth conditions for the logical terms. What the moderate inferentialists really want is that whatever rules of inference we follow regarding conjunction, negation, and the universal quantifier restrict the class of models, so fix the class of models that satisfy these conditions. So if a model satisfies these three conditions, it should be in the class fixed by the rules, and if it doesn't, it should be out, and that class is called standard, ST, here in Fractal. So this is what the moderate inferentialist needs, that whatever rules we follow, they entail these clauses, the validity of these rules entails these clauses, and therefore they pin down the right class of models. Does it happen? Well, let's look into it. Here are the natural deduction rules for a negation and conjunction. One might think that natural deduction calculus is the most natural representation of the rules of inference that we follow. So let's think about that for a minute. The rules for negation are the ones I already presented, the introduction rule and the elimination rule. The first one was the meta inference, the second one was the double negation elimination. And the rules for conjunction are the ones you see here, introduction of conjunction and the two eliminations. How do they constrain the class of admissible interpretations? Well, by being correct, therefore by being valid. The first line here expresses the validity of conjunction introduction, and the other two of each elimination rule for conjunction. Now you can see how these statements, the first one says, well, if the conjunctions are true, the conjunction is true. And the other two say if the conjunction is true, then each conjunct is true. So put together, they entail the intended truth conditions for conjunction. And therefore, the class of interpretations that these rules fix are those in which this intended truth conditions hold. And therefore, the rules for conjunction fix the intended meaning for conjunction. And this is a big win for the moderate inferentialist. How about the rules for negation? Do we also win here? Well, we already saw the constraints that these rules impose, right? And as it turns out, they follow from the intended truth conditions, the constraints, but they do not entail it. So they're not equivalent. What we get is that if a negation is false, if a formula is false, then its negation is true, but we don't get the converse of that. A way to see it is by realizing, for instance, that models in which every sentence is true satisfy both constraints just by going back very quickly. Here, this constraint, if everything is true, then obviously this consequent is going to hold. And if everything is true, then this consequent is going to hold. There is another case here that I present, M2, the models that assign truth to every propositional tautology and false to everything else. Those also satisfies the constraints. So what we learn from this is that the validity of the rules for negation don't fix the intended meaning of negation. So the rules for negation don't fix the intended meaning. And this is a big problem for the moderate inferentialist. But they appear to have a way out, and that is to say, well, the natural deduction rules don't really do the job because they don't really articulate properly the rules we actually follow. For that, you need a stronger calculus, a more complicated calculus, perhaps a sequent calculus or a bilateral calculus, something like that. Let's do sequence. If you don't like it, you can think in terms of bilateral rules. The rules for conjunction and negation in standard sequent calcula are these. I think you're familiar with them. The constraints they impose are going to be slightly more complicated because of the reading of a sequence. So here we can see, for instance, the constraint that the rule of introduction to the left, the rule of negation introduction to the left and negation introduction to the right impose these two constraints, one each. And here, of course, what we need is that if a sequent is valid if whenever the antecedent is true or everything in the antecedent is true, something in the succedent, is true. So this means that something here is true. These two constraints put together happen to be equivalent to the standard truth conditions that we wanted. So they are equivalent to a local constraint. And therefore, we can say the sequent rules for negation do fix the intended meaning of negation. Everything is nice. Now, I didn't come here. So yeah, conjunction also works. Everything is good. But I didn't come here to talk about negation and conjunction. I came here to talk about the quantifiers and first order quantifiers. So let's focus on the sequent rules for the universal quantifier. They're typically these. This is like the elimination rule. If we have a universal claim, we can infer any instance. This is like the introduction rule in natural induction. If we have an arbitrary instance, so if C is an arbitrary constant, it doesn't occur in gamma, delta, or phi, then we can infer the universal. What constraints do these rules impose? Well, this is just the same as for negation, but applied to this particular case. This is horrible. It looks horrible. I don't want to read it. So here's we can express it most succinctly as follows, using S for L and S for R. So the L is the L and the R is the R. They're equivalent. What does S for L say? Well, it sort of expresses this introduction to the left rule. If a universal claim is true, the validity of it, sorry, if a universal claim is true, then each and every instance of it is true in a model. And this is a local constraint. It's a very nice, easy constraint. No problem. The problem is with the other rule. Let's look at this second constraint. Let me write, so here I write M prime equivalent CM to express that M and M prime assign the same truth values to every sentence in which C doesn't occur. So I'm going to call them C neighbors or C nearby moles. What this statement, this constraint says is that a model has to verify a universal claim whenever every C nearby model verifies this particular instance, where C is an any arbitrary constant, any constant that doesn't occur in phi. So in other words, if every model that is similar to M in the sense that it assigns the same truth values to every sentence except the ones that contain C, says that phi of C is true, that is because everything is phi. This is a weird clause. We can see how S for all L and S for all R follow from the standard clause that we want, but do they entail it, or what conditions do they impose? And the problem with S for all R is that it's hard to parse because it's impredicative. As you can see here, we have that quantifier. So if I want to know if a model satisfies this condition, I first need to know what the C nearby models of that model are. So I need to know what other models I have in my admissible class, right? And in particular, I need to know if they assign the same truth value to this sentence, because this sentence doesn't contain C. And that is, of course, circular and problematic. Very problematic. This clause doesn't obviously, unlike this one, doesn't obviously impose a local constraint on the class of models. So a better way, perhaps, of thinking about the question is to ask which classes of models fit this. So to think in terms of classes of models rather than models, isolated models, to see if a model satisfies it or not. It's not a good idea. Let's focus on classes of models and see if the class fits the condition. And so basically what we're asking is this. What class of models M can I put there? Can I make this quantifier range over so that every model in this class satisfies this condition? And moreover, I'm also interested in the question, which classes do that and also satisfy the other clauses entailed by the rules, the nice ones? So which classes satisfy all of these four statements, conditions? The hope is that the answer is just one class, the standard class, ST. Let's see. So here's the reason why I'm presenting this paper in this conference is because it uses a lot of fixed point constructions and is inspired Kripke and his fixed point constructions. I didn't know it was a conference on truth at the beginning. I'm really sorry. So how can we use fixed points to understand what this constraint is, what constraint the rule is imposing? Well, say we begin by hypothesizing a class M of models. Then we can improve it by applying this jump operator. What does this operator do? Well, it says, look, I'm going to look into this class and see which models in that class satisfy this condition. Whenever all the C nearby models say that phi of C is true, that model says for all V phi is true. And I'm going to remove the ones that don't satisfy this. Of course, once you remove some models, other truth values might have to change. So it's not that one jump is enough to improve things, because once you got rid of some models, what happens now is that perhaps for other models that were already there, this condition becomes true for another phi, because now there are fewer models. Before, not all the C nearby models did this, but now, because we got rid of some models, like it is the case that all C nearby models do this, and so on. So we need to apply this several times, this jump several times, until we get a fixed point. So this is why we obtain a sequence of increasingly more fitting classes of models. The first one is the one we started with, then we apply the jump to obtain the successor, and at limits we take in the intersection of all the previous stages. And obviously, any fixed point of this sequence, of any such sequence, will fit S for all R, will satisfy this condition. As it turns out, every sequence reaches a fixed point. I am not going to stop here because we lost a lot of time with the poor connection. So I can come back to this Q&A if people want. But believe me, this is the case. The sequence is monotonically decreasing. Cardinality considerations entail that every sequence reaches a fixed point. I am interested in this particular class of fixed points, which is the admissible fixed points. What is an admissible fixed point? It's a fixed point that also satisfies the other nice clauses that we want satisfied. The clause for negation, for conjunction, and the local clause that says that if a universal claim is true, then all its instances are true. Now, here are some small fixed points, admissible fixed points. The empty set. The empty set obviously satisfies all these constraints and is a fixed point. It's a matter of just checking. So it's the minimal admissible fixed point. Are there other fixed points? Yes, here's another small fixed point. Any singleton of a standard model that has exactly one thing in the domain. We can explain this if you want Q&A, but now I have to gloss over that. Are there any other kinds of fixed points? Yes, there are. And for that, I need to introduce some notions. You know this one, maximal consistency, obviously, which I'm going to call MC. A set is maximally consistent if its negation consistent and complete, and moreover, it's closed under logical consequence. The one I am more interested in here is the notion of N maximal consistency, which is something I made up, but it's useful. I'm going to call it NMC. Well, N is just any natural number. The first condition is the same as before. The second condition is slightly different, and it says the following. The set gamma that is N maximally consistent has to be closed under all the rules of the calculus, under N many applications of this rule for all R, plus all the other rules of the calculus. So if it's 0 maximally consistent, it will be closed under it. So to be 0 maximally consistent, the only requirement is that it's closed under all the rules of the calculus except for R. If it's 1 maximally consistent, it has to be closed under all the rules of the calculus, plus one application of R, and so on. And here's some horrible notation, which is kind of easy. If M is a model, gamma M is its truth set, so the set of sentences that are true in the model. That's just easy. If Fractal M is a class of models. I'm going to call it MC complete if every maximally consistent set is realized in the class. So if every maximally consistent set is the truth set of some model in the class. And finally, MC is going to be the name of the class of models that have a maximally consistent truth set. That is all the preliminaries, notation, etc. Now for the observations, a very simple one is this. If a model satisfies the standard clauses, the intended clauses for negation, conjunction, and S for all L, which is the elimination rule for the universal quantifier, basically, its truth set is zero maximally consistent and vice versa. So saying that the truth set of a model is zero maximally consistent is the same as saying that the model satisfies these nice clauses. A second observation is that if a class of models is MC complete, so if every maximally consistent set is realized in the class, then all the models that have a maximally consistent truth set in the class survive the jump. So if I apply a jump to M, all the models that had a maximally consistent truth set will not be ruled out. An immediate corollary that we get from this is that MC is an admissible fixed point. And the reason is that, first of all, MC is every model in MC has a maximally consistent truth set by definition. But if a set is maximally consistent, it is also zero maximally consistent because it's closed under all the rules of the calculus. And therefore, it will satisfy the nice clauses, and therefore it will be admissible. And it is a fixed point because of this observation, because it is MC complete. And so none of its models, all of its models are have maximally consistent truth sets. None of its models will be ruled out by a jump. So a jump will preserve MC intact. And therefore MC is a fixed point and it's admissible. But another fixed point, interestingly, is the class that the moderate inferentialists wanted, ST. And why? For the same reasons. Every truth set of models in this class is maximally consistent, and moreover, the set is MC complete. One last thing in terms of results. So if a class of models is such that every model has an N maximally consistent truth set. So if all the truth sets of the models in M are N maximally consistent, then all the truth sets of the models in JM, so in the improved version of M, are N+1 maximally consistent. So J improves the truth sets of the models by making them more closer to maximally consistent. A corollary is that wherever we are in a sequence, if we have at some point that every model has an N maximally consistent truth set, then after omega steps, every model will have a maximally consistent truth set, period. And a further corollary of this is that if M is an admissible fixed point, so an admissible class of interpretations that is a fixed point of J, then the truth sets of all the models in M will have to be maximally consistent. Just because if it's admissible at some point, if it's admissible, then all the truth sets are zero maximally consistent, and after omega steps, they will be maximally consistent. And so if it's a fixed point, omega steps don't change anything. So they were already all maximally consistent. And so the obvious corollary is that MC is the maximal admissible fixed point. So we have lots of fixed points. Now you know a bit about these fixed points. I want to extract one consequence, and here's the main philosophical question. as far as moderate inferentialism is concerned, I think that there are only two possibilities here. Possibility number one, the rules that determine the meaning of negation, conjunction, and the universal quantifier fail to pin down a unique class of models. The other alternative is that they do pin down a unique class of models, but it is unintended. And I'm going to explain why these are the two options. So let's focus on the first possibility first. Note that every admissible fixed point of J satisfies the truth clauses fixed by the rules that determine the meaning of negation, conjunction, and the universal quantifier. It's because they're admissible, so they satisfy the clause for negation, the clause for conjunction, and one of the clauses for the universal quantifier. And in virtue of being a fixed point, they fit the other clause for the universal quantifier. If the rules, as the inferentialist says, is all we have to determine the meaning of the logical terms, then nothing can decide between these admissible fixed points. Every such fixed point is admissible. Now, if this is the case, then we must conclude that the rules of the calculus are not categorical. In the same sense that we conclude that first-order arithmetic is not categorical. The intended interpretation is among the interpretations, but there are others. So here, the intended class is among the classes that are admissible, but there are others. The empty set, the set of maximally consistent models, and so on. So my conclusion in that case would be there is some indeterminacy involving first-order quantification. The second possibility is that it's something that has been suggested to me by a friend of mine, Bruno, from Buenos Aires, Bruno Larre. He says, look, no, there is a way of extracting a local condition from all the rules of the calculus put together. The rules of the calculus put together happen to tell us that some inferences are valid. Basically, whenever we can derive from them a sequence of the form gamma, sequence, symbol, like turnstile, phi, they're telling us that that ordinary inference from gamma to phi is valid, right? And so why don't we put together all those ordinary inferences that are derivable by the rules, and we focus on the constraints they impose. Since they're ordinary inferences, they impose a local constraint. And so, in fact, they can be seen to fix the class of models in which all the ordinary inferences, all those ordinary inferences are valid. There must be such a class. Call it M. Now, what is that class? Well, MC is the largest class of models that fits the truth clauses that in turn express the validity of the rules of the calculus. From this, we can infer that MC is also the largest class of models that validates all the ordinary inferences that can be derived from those rules. It's like a soundness argument. So in other words, this mysterious class M is MC. Now, if the moderate inferentialist takes this route, they will have to conclude that the rules that determine the meaning of negation, conjunction, and the universal quantifier in our language fix a unique class of models, and that is MC. But notice that MC is not the class that we wanted, right? It's not the class that they wanted. The class that they wanted was ST. So what happened is basically that it's not a categoricity problem. So this is no longer a categoricity problem. It's not that we have many possible interpretations. Some are intended, some are not. We have only one interpretation. So one meaning, one class, and it's the wrong one. So I don't know which is the right way of thinking about this. And I would be very happy to hear what you guys have to say. And I'm done. Thank you.